In physics, motion is never random. Every movement unfolds under forces, constraints, and conservation theories. Now, watch this sink. It looks like a tiny accident, but it is also following rules. The drop stretches, hits the surface, folds into itself, and then blooms outward in delicate threads. You can see viscosity, temperature, and turbulence, they all are playing their roles. An AI model is no different. Beneath the surface, there lies a field of probabilities, and every prompt that you write sends ripples through it. Every time you speak to an AI, you are not chatting with a robot. You are disturbing a liquid which is made up of meaning. Under the hood, your words are becoming your coordinate. They are points in a huge, invisible landscape which is basically built of everything that humans have either written or said or even chatted on a social media. Think of it as a map of civilization. News article, research, novels, memes, and everything compressed into patterns. Most of us were taught that words are labels. This word means this thing, and that word means that thing. But to a modern AI, word is more than label. It's like a distance and direction. The gravity is closer to Mars. It's closer to Einstein. Change the meaning. The entire context gets changed. For example, if you pull gravity near romance or love, it will become a poetry. Now here's the catch. If you don't know where you are on that map, your message will behave like this ink. Beautiful, but uncontrolled. It blurs, the signal gets lost in the noise, and in physics we call that it's an increase in disorder entropy. A layman would say that AI didn't get me. Today, we are going to do something very different from a normal AI tutorial. I'm not going to show you some crazy AI tools or some dashboards to monitor how AI is being used. I am just going to pop the hood and show you the engine block. We'll look at how a machine actually transforms your words into thought, how it turns speech into numbers, how it decides what to pay attention to and what not to pay attention, how it settles down on one answer from like millions of possibilities. We'll talk about ideas from physics, and my intention is not to intimidate you, but to give you a language for what you already know about, right? And I want you to understand the feeling when the AI is on fire versus when it is dull. So, this is not a prompt engineering course, this is basically the thermodynamics of language, how information flows, how it compresses the data, how it releases energy in a certain fashion that happens to speak. So, if thought had physics, then every prompt that you write is an experiment. Well, you set the initial conditions, you define the boundaries, and the model responds by running the law it learned from the context. And here is the good news. You don't need to be a PhD to play at this level. You just need the right mental picture. By the end of this video, I want you to feel not like a passenger pressing buttons here and there, but like a master architect. Someone who understands the structure well enough to shape it on its purpose. So let's begin. Now let's slow down and define what AI actually is. And let's start with a large language model, an LLM. An LLM is not a magic brain and it's not a simple database. It's a transducer. That word sounds technical, but the idea is simple. A transducer is any device that takes energy in one form and converts it into another. Like a microphone does this. You speak, the air vibrates, the microphone turns those vibrations into an electric signal. A speaker does the opposite. The electric signal comes in and the sound waves come out. Same pattern, the energy comes in, transformation happens, and there's an energy that comes out. Now, an LLM is a transducer for language. It takes your words, breaks down into small pieces called tokens, and these tokens are the input energy. Inside, it converts that into a different form, a cloud of numbers that represent meaning, and then into prediction about what next token is going to be. So it's like this: there is an input which is text, and an output which is like most likely continuation shaped by everything that it has learned. So, in order to do this, LLM needs a sense of space. That is where word embeddings come in. Uh, Let me explain this concept with an example. Imagine a giant room where every word you know is a glowing dot hanging in the air. Words that are related sit close to each other. Like, for example, king and queen sit just a few centimeters apart. King and president are nearby. King and engine are far away. This is the geometry of meaning. When a model trains, it figures out where to place each word. It does that so that the sentences it has seen before make sense as little path through this room. So when you type a new sentence, you're drawing a fresh path. And the model is now trying to guess where that path is likely to go next based on what other paths it has already seen. Now we are going to add the next concept, which is all about transformer. Most of us read a word from left to right, barring some languages where there is also right to left, but the transformer doesn't. It doesn't follow a certain direction. It looks at an entire sentence or even thousands of tokens at the same time. Now, what happens inside this transform? There is a process, a mechanism known as self-attention. Inside the transformer, this process happens. Self-attention is basically model asking constantly for every word, what matters to me right now? When we talk about self-attention model, mechanically, we are going to talk about three things: query, keys, and values. Or you can call them as QKV. Now, the query is the question a word is asking, like, who is my subject? Or what time are we talking about? The keys are what every other words offers. Like, for example, a name tag might be saying that I am a person, or it might actually say that, I am actually a place, or I might be actually a verb about time. And then the value basically is the information that each word will pass once it has got your attention. So, what does this self attention means? Self attention is then the matching of these queries to keys to decide what values to focus on. Now, the model does this many times in parallel. Like, these are different heads in many directions that are already happening. One head might focus on grammar, other might actually focus on reasoning, and the other might actually focus on the way I have to respond, like the tonality of the conversation. Let me give an example. Let us say this line: CEO thanked the engineers because they solved the outage. Now, when the model processes this line, the word they, it has to decide that, like, who are these they have to refer to. Now, this word they will be generating a query which earlier group performed the action solved, right? So it's trying to reason now. Now, earlier words, there are keys that have come out, right? So, for example, the keys are like CEO. CEO is like what? It's a singular person, an executive role. Engineers, that could be a plural person, and again, technical role. And then outage is basically an event. So these are the keys basically: CEO, engineer, outage. These are the keys. Now the query from they matches more strongly with the key from engineers, right? Because they is plural and the CEO is not plural here. And that is the semantic linking to solving outages. Now comes the crucial part. The model doesn't just select the word engineers, it pulls in the value attached to it. Information like plural human agents, technically capable people, likely people will solve a system failure problem, right? So in simple term here, Q is equal to who solved the outage, which is the query. K is equal to plural technical people, right? Relating to engineers. V is the value, which is basically confirming. Or we, the engineers, are the agents who have fixed the outage. I know it's getting a little tough to understand, but it's basically a complete circuit. There is a question, there is a match, there is a transfer, meaning combining into understanding. If that sounds abstract, picture gravity. Some words pull on each other strongly, others barely intact. There is no attraction towards them. So the attention score is just like a little gravity meter. Higher the score, stronger the pull. Higher the attention between two words, higher the attention score. Now, what are these tokens that we spoke about? A token is basically just a chunk of text. Sometimes it can be a whole word, sometimes it can be just a part of word, sometimes it could also be punctuation. Roughly 1000 tokens is probably around 600 to 750 words, English words, right? So when you hear that a particular model can handle 2 million tokens, think of it as a huge whiteboard where you can probably just paste or pin equivalent of maybe around 20 to 25 novels at once. And model can see and reason all those words, all those contexts in a single pass. Imagine the sort of volume it can process. Now, this is where I'm going to introduce the idea of enthalpy, which is a borrowed idea from physics. What do we call enthalpy in physics? Basically, we talk about how much energy is stored in a system. And you also take into account for the environment. Like, for example, the heat content of a pot of water on a stove at a particular temperature and pressure. So the environment, temperature, pressure, and a certain condition comes into play. You don't need to understand the full equation. Just understand the intuition. It is basically the system's capability to absorb and release energy while staying in a usable state. Now, how do we apply this concept into an LLM? For an LLM, the context of a window, which is basically the amount of text it can hold in its active memory, is like an information enthalpy for that LLM. The bigger the window, the more heat from your documents and prompts it can hold at once. And then it can work on a probable reply for you. Now that brings to the different model types. And you would have heard of it, right? GPT-5, a high context model. It's basically like a heavy reactor, and that is built for like deep, complex, high stakes reasoning. However, just like a big reactor, it uses a lot of compute, like a nuclear power plant generating a massive amount of power, right? But it requires a lot of energy also. Similarly, a smaller context model, like for example Gemini Flash, that is basically built for only speed and efficiency. Heats up fast, cools down fast, and is perfect for smaller and simpler tasks. So when you pick a model, you are not just choosing a brand, you're actually choosing the energy profile. You are actually asking how much thinking heat do I need? How long am I willing to wait? How much am I willing to spend? Right? So all these questions are also coming into play. However, underneath it all, these all systems are following a simple procedure. They're basically trying to eliminate surprise. Mathematically, they are picking up the next token that fits the pattern. Physically, you can picture it as a system rolling downhill on a valley, settling into a stable shape. And just like in physics, your initial conditions also matter. A vague, noisy prompt can pump in a lot of messy energy. Like model has to work a lot harder to think if your prompt is not perfect, right? It takes a lot of time to settle down on the right context that you are actually looking for. And then it falls into trap of giving you a very generic answer. A clear, well structured prompt actually feeds in energy in a very controlled way. And the system then settles down into a very sharper, more specific value. I mean, oh, you mean this? Like, system understand the question. Once you see the model as a transducer managing informational energy with a limited enthalpy budget, you stop treating it as a magic box. You start treating it as an engineered system that you can design. Let us say that you write a marketing plan for my new watch. On the surface, you feel that this sounds reasonable. I'm asking a reasonable question. You already told AI what you want, right? You want a marketing plan. You told a product also. It's a watch. But now think from my model point of view. You're like walking into a library which is size of a planet and asking, bring me a good book. Inside this huge multidimensional space of words, marketing is a huge foggy cloud. It is basically including everything from like memes, Fortune 500, go-to-market strategies, B2C, B2B, performance ads, films, growth hacks, social media, billboard, ATL, BTL, email funnels, CRM, pricing. A lot of things are already there. Watch is another cloud. Like there are a lot of watches, luxury Swiss timepieces, smart watches, fitness tracker, even cheap fashion watches in the malls, vintage heirlooms passed down from grandparents, and each of these have their own audience, price point, and a different sort of emotional story. Now, the model tries to find an overlap. But you haven't told the model, is this watch going to be a $50 watch or a 5,000 watch, right? Is it going to be for a teenager, or is it going to be for somebody who's a 60-year-old, or is it going to be for a CEO? Are you talking about a digital watch? Are you talking about an analog? Or is it like a jewelry or a real luxury item to look for? So you have given a big, giant, fuzzy shape and no coordinate. So from physics perspective, this is high entropy problem. There are too many possible words that could fit your sentence. Now, the system has to dissipate a lot of uncertainty to land anywhere, and you literally have to pray that it lands to the context that you are really thinking in your head. So, what does it do? It takes the path of least resistance. It goes to the statistical center of all the marketing plans it has seen around marketing and watch. The safest, most average value in the entire landscape. So it might give you something like define your target audience, highlight your USP, or what are the KPIs you are measuring, what are the results that you really want. And it asks you this question because now it has to answer you for the right context. And now you read it and you think, wow, this is really, really boring. And AI has gone nuts and crazy. It's lazy. AI has been lazy. I should just do my work on my own. But the AI is not lazy. It's basically being honest. You gave it a very high entropy question and it gives you a very high entropy answer. The AI is also yearning for a resolution for your question, right? That kind of low resolution blur that fits almost everything and gives you nothing won't actually give AI also a satisfaction of giving a right answer. But if you now start thinking like a scientist, solution becomes really clear. The answer lies in reduced entropy. Now think about this. Add an entity. You say you are a luxury brand strategist who has worked with Rolex and Patek Philippe. And now you add constraints. This is a $7,000 mechanical watch hand finished in Japan. And it's limited to say 700 quantities a year, and we are aiming it at successful CEOs and entrepreneurs in their late 30s who basically have started appreciating craftsmanship, luxury, and design minimalism. And then you add further context, a bit localized context, which is not basically present in that entire three-dimensional space AI is scrolling, but you add a little bit more context to it, right? A small window. And what does its small window contain? Here are 5 PDFs of competitor brands. Here is our brand story. Here is all the stuff about our founder. Here is the stuff about our price ladder. Here is what our early consumer feedback looks like. So every piece of detail that you are now adding is now tightening the lens. You are removing worlds where the answer could live so model can settle into the right. This is what I mean by thinking in physics, not feelings. When your prompt is vague, the model's information energy is spread and it basically relaxes into a very average pattern and you never get the answer that you really want. When your prompt is sharp, your energy is focused and the model can also do a precise one. So the machine is not disobeying you. It is obeying the only laws it knows, statistics and structure. Your job is to give those laws something interesting to work. Now let's rebuild that same request like an engineer. Instead of throwing a bucket of water at a machine and hoping it forms a river, we're going to carve a channel and tell the water where exactly it has to flow. Step 1, identity. We start with act as a luxury brand strategist who has worked with Rolex and Patek Philippe, and you specialize in making heritage watches, you great in storytelling, and you also understand boutique distribution. That single thing does something very powerful inside a model. It moves the starting point of the conversation to a very specific neighborhood in the knowledge space where the AI is now crawling across luxury, long term brand building, craftsmanship, high net worth customers, and a boutique sort of like a keyword. Now you start adding constraint for AI to further narrow down, right? So let us put a constraint like use a particular stage gate innovation framework or a product genome framework. I'm going to talk about product genome framework in my later videos, but let's just hold on to that thought for now. It's an innovation framework to build software products that applies for hardware products as well. So now you break that watch into positioning, right? So you start talking about heritage, craftsmanship, you talk about scarcity, you talk about luxury, and you also start talking about functional traits like you want a movement accuracy, you want maybe water resistance, or you might want even smart features. And then you talk about distribution strategy, looking at flagship store, e-commerce, maybe perhaps a boutique partnership or something like that. And then you talk about audience phenotype, something like, collectors, aspiring professionals, entrepreneurs, multimillionaires, so something like that. To a human, that sounds like a lot of marketing jargon, right? But to the model, it is a skeleton. It now knows how to organize your answer. These are the buckets it was looking for. These are the levers with which AI is going to play around and find you and give you the right answer for your question. Now, step 3. Oh, it's all about context reservoir. Now, what is this context reservoir? Imagine feeding them a real data. So, here are 5 PDFs. First PDF Omega, Grand Seiko, Cartier, Apple Watch, another mic brand that you admire, and JTM strategy, or maybe even give you a ebook that you have heard about them. And it can actually extract their price ladders, it can extract some brand codes, and there must be some information about their GTM channel mixes and the mistakes they have done. So give that information, and that particular information acts as a context reservoir. It is something like filling a tank with a high octane fuel instead of random liquids. Now the model has a concrete example to compare against, not just vague memories. So it will now act persistently consistent. Final step, objective. So now you clearly define what you want. So for example, you might ask that I'm looking for a 12 months GTM plan for a $8,000 mechanical watch. It is built in Japan. I want 700 pieces a year, and this is aimed at professional who are successful entrepreneurs, CEOs, software engineers in their late 40s, people who really love precision and minimal design. Now you're also specifying the next request. You can ask them, include launch phases. Talk to me about the hero campaigns. Talk to me about what kind of content format I should use. Call out some anti patterns that could probably damage the brand and lower down your revenues. Do this and now watch what happens inside the machine. Now, let's look into some patterns that the machine is going to go into. The first, words like heritage lock into something like a founder story. Behind the scenes atelier shots. Engineers in their 40s, they activate concepts like, tech conferences, founder podcast, and those sort of like genius in their 40s and founder podcast, those words are actually lying closer to each other in the three-dimensional space because that is how the data has been built over the period of years. AI has crawled and AI has found that when it looks for engineers in 40s, tech conferences comes in play, founder podcast come in play. A deep down YouTube breakdown might come into play. It might not show you Insta reel or generic TikTok dances, right? So the model self attention mechanism is tightening now. The self attention score has really increased. You, the smart prompt architect, has actually helped AI to increase the self attention score to a highest level possible, and now it is going to behave according to you using minimum amount of entropy. So instead of spreading the focus area around everywhere in the internet about marketing and watches, it now concentrates into a very narrow band of example that fits your description. So entropy drops. The information energy you have poured now has walls to bounce off. Now the thinking starts. And the result that comes is a very sharp, structured plan. You will get story arcs, you will get channel by channel GTM strategies, you will get content calendars, you will get price gates, you get loyalty mechanisms, you'll get probably even a business plan. And it will also give you steps to avoid, if you want to stay premium. So from the outside, it looks like just a prompt. But under the hood, you have changed the entire physics of the system. And this is very important for you to understand once you start talking to AI for all of your tasks. Engineers never rely on vibes. We design boundary conditions, we supply controlled energy, and then we measure outputs. This is what great prompting is really. So you didn't just type words, you typed it in a way that respects how the engine really works, and that is really important. So once you understand how a single prompt shapes the entire physics of the model, the next question is, what next? Should I just stop at this and this is all about AI? No. There's a lot that you can now do. I mean, you have just asked question. Probably now it's time for you to ask AI to perform certain actions. Right now, people are using AI like a very fast intern. You ask question, it will give you an answer, and every interaction is like a simple experiment for you. But the smart have started using AI to even perform their day-to-day monotonous repeatable tasks, and there are a lot. And this is what agentic AI is all about. Agentic AI, it asks a very different questions. Like, for example, what if the system could hold a goal in mind and work towards it towards time. Right? So, for example, how can a system use your memory, your tools, and the feedback that you are providing on a regular basis, almost like a small company of few people working for you, and they never sleep, and also they never complain. Let's look at our watch idea, and now let's just extend it to a bit further and try to see how can we implement agentic into it, right? So now we don't just say write a plan, right? So we actually now define a goal. We now say help us design and launch this $7,000 mechanical watch, and help us get Q4 with 25% boutique sale through, and 10,000 pre-registrations from our target users, right? Then we give the AI platform some tool. So for example, we'll give access of web browser. Now just use the web browser for research. And we also might give a spreadsheet engine. You need to model some sales and footfall targets for us, and also demand projection needs to be built. You also give a PDF reader. You know what, you need to go digest all the competitor reports, news, research reports about this industry, and top it up with some design tools. So you might actually give some design tools to create mock-up campaigns, or maybe you can actually take given access to your email system and CRM, maybe in a sandbox at this stage. Now, once you have given the access to the tools, you start giving it a memory. You need to give a memory where it can start storing what it learns, right? There are a lot of things like brand codes, past campaigns, customer interviews, pricing experiments, living knowledge, and that knowledge base needs to be updated at a regular basis, because the news research reports, they're always updated, and you might be adding a lot of context through your emails and other things that you're putting in the system. So you have architected a loop. The first part is the planner. It breaks the goal into few tasks. First task is, for example, find potential boutique partners in 3 key cities. The second task could be model revenue scenarios. Third could be, let us look into the launch events, right? And then it will talk about drafting some drift email campaigns for those customers. And then a calendar for social media or even the email marketing would come into play. So once this entire planning part is done, the second part for the agentic would be the executor part. Now it actually starts running the tool. Like for example, it searches the internet and it fills the spreadsheets that you have given access to. It starts drafting the documents and email, and even the email campaigns that you have been thinking about. There is another part to it. It is also a sort of like a devil's advocate or critic. It is going to check the work. Does this matches the brand? This is what user has actually asked, or this is out of context, or and are we maintaining the premiumness in terms of our brand value, brand positioning that we are actually putting in a plan. Also, are these numbers making sense? Am I giving like $100 billion revenue instead of giving something like a $10 million revenue? So these are the things that the critic is going to analyze. Finally, there is going to be a memory where each cycle of work is stored, so that system gets little less surprised every time a new information comes in. If this feels abstract right now, think of a thermostat in your home. It just doesn't heat blindly. It first senses the temperature, and then it compares with the target that you have given, and it keeps adjusting the system on, off, higher, lower, in a feedback loop, so that it gets to the target that you have. An agent is that idea on steroids for knowledge. It senses where you are related to where your goal is. Subscribers, like number of leads, awareness, revenue, and then it start taking actions, right? Intuitive action, and it also start measuring the results. Update your internal picture, and then tries again until unless the goal is achieved. Some of the goals might not actually be achievable, like revenue probably might not be achieved by a solo agentic AI system. From a thermodynamic point of view, you have built a machine. This machine continuously reducing entropy over time instead of a single shot. It's a continuous feedback loop. Instead of give me one answer now, you are saying keep working on this until the big picture sharpens. So your role changes. You now become the architect of the system. You now define your goals, you basically set the tools, you define the boundary condition, you give more enhanced context. Now let's just make this a little bit concrete. How would you actually build an agent like this with today's tools? At the simplest level, you can do this inside a hosted tool like ChatGPT or probably an app like Relay. I'm going to send the link of Relay app here as well. In a ChatGPT, you might actually set up a custom GPT or system configuration. I mean, you can go to ChatGPT, you can find custom GPTs, and you can create a new custom GPT. And you can actually, when you actually create a new custom GPT, you will actually be asked for a system prompt. So give a system prompt something like this. You can define that you are an agentic AI system and you have a goal of launching a $7,000 mechanical watch made in Japan for engineers and maybe for CEOs. And then you further write that your task objective is basically to plan and research about competitor research reports, competitor planning, competitor performance, and then you should also be doing content drafting tasks, content drafting steps to hit probably a 25% sale target through boutique channels. And then our goal, and then add that our goal is 10,000 users pre-registration. So now you define tools. You connect things like browsing, file upload, maybe a code interpreter, or even a spreadsheet. You tell the model exactly when to use which tool. You describe the loop in this way, like something, you can write something like this. When given the overall goal, break it into these tasks. For each task, and you can write the task. For each task, propose a plan, execute with these tools, learn, and then suggest what to do, like what is the next task to be done. I mean, you can write it in your language. I'm giving a sense of what you need to write. And you can always give an instruction that you need to write a short status report at the end of each cycle. Then you upload your PDFs, competitor, brand story, pricing, and all, and instruct continuously refer to these documents. Never invent pricing or brand details that are never not given to you. So we are sharpening the knowledge that these are the documents you have to look into. So now you have built a very simple agent. It just plans, acts, reflects, and repeats. So this is going to do a lot of repeatable tasks that you probably would be doing with multiple prompts. Like you will definitely be asking ChatGPT all these questions, but now you have created an agent that is going to do the same for you within ChatGPT. So now let's look into how it will actually work in an app like Relay. So a Relay is like a workflow builder, and I'm going to show you a screen in which you will now see how Relay looks. You can even go one level deeper and probably turn this into a visual engine, right? So it's a sort of like a visual workflow builder engine. You can create workflows in Relay, and for example, for this agent, we can create an AI agent. Let's call it as a launch agent or a watch launch agent. So there are a lot of nodes in the Relay. So we start with a goal node, like where we probably hard code our initial target, which is about launch timing or sell through, pre-registration, something like that. Then once we have defined a goal node, we will define the next node, which will be a planner node. Now the planner node needs to be powered by the LLM of your choice. Why? Because the planner node is going to do a lot of reasoning like a human and would require an LLM for that. So give that particular node a prompt of something like, given the goal and past memory, break the work into 3 to 7 concrete tasks for this cycle. So now you have already given the planner node a prompt. So this prompt will be given to a ChatGPT or whatever LLM you connect, and the goal is already defined. So it flows into that context. So now once you have done that, you have actually, what you have done is you have already added a goal node, you have added a planner node. Now you go and you add an executor node. So what is this node gonna do? This is going to call all the tools, your browser, your spreadsheet, your email drafting tool, or a document analyzer. So for this, you can define a job, something like for each task, pick the right tool and produce the right outputs, and you can define all the outputs you want, list, model, drafts, whatever you want. And then it's very important that you have something like a critic node, and we spoke about the critic as a fourth step when we were talking about the steps for agentic. So the critic node needs to review the executor output against the constraint and the goal defined. And there could be many constraints that you need to define. Something like the brand consistency, the brand guideline that the design might not be followed. Or something like, does it respect your luxury position? Are the number plausible? You now add the last node, which is basically the memory node. Now you need to connect this memory node to probably a database or like a node store where you can actually capture all these learnings and summary, probably like Notion or Google Docs or whatever tool you are comfortable. Finally, now sequence them and wire them in a loop. Start from the goal node, go to planner, then it goes to executor, then it goes to critic, then it goes to your memory and planner again, with human in the loop. So human in the loop is an interesting thing. Once you actually start making AI agents in Relay, there is a human in the loop option, which is really good, because you actually get to see and evaluate the work and don't just rely everything on AI. So I really recommend you actually toggle the human in the loop when you make an agent at a particular step. So once this is saved, pressing run will just not give you a one shot answer. It starts a controlled process. Now you can watch, steer, and refine, and then you can actually give a schedule to run this process also on a daily basis. This is where this series is heading. We are not going to make videos about what kind of prompts you should write for different kind of AI, right? It's not just about better prompting. My goal is to basically give you knowledge and information in a way that you actually understand the entire system and not just what to do and how to do on that particular system. And that's why we are talking about AI systems in a way that you actually get to see under the hood what is happening. So now I understand that this is a lot to process while you are staring at a screen, and I don't expect you to remember everything that I am sharing and also the metaphors that I am probably using. So that is why I am launching Decode with Anand, a podcast show which is basically built for on the go builders. Think of it as like a high bandwidth audio show for people who basically like to think deeply when they are on the go, traveling or driving, and so on. So I'm planning to include a long form conversation and solo episodes that would unpack ideas from topics like AI, quantum computing, technology, business, economics. And I would like to present these ideas in a very different scientific slash plain human language mode for you guys. So this won't be flashy visuals or dopamine gut kicks and all, but this will be mostly chemistry of ideas, voice, and silence. And you'll find this podcast sooner on Spotify, Google, and Apple Podcast. You can put it on when you're driving, walking, or winding down at night. So far, we have treated this like a world of pure math and metaphors. Attention models, entropy, agents, and whatnot, right? But there is a very real physical machine underneath all this. This cloud is not just cloud, but it is actually sitting in a machine. And to understand what that is, we really need to talk about a difference between a CPU and GPU in simple, honest terms. So let's start with the CPU. What is a CPU? CPU is a central processing unit, and you can think of it as a single, incredibly smart chef. It can handle a lot of different recipes you can throw it, and it can switch between tasks quickly, make complex decisions. If this, then what? If that, then what? And it has few very powerful cores and big caches of fast memory, and is brilliant at doing one complicated thing, which can be sequenced one after another, and it will do it in a very precise manner. Now look at what modern AI does. At its core, running an LLM is mostly one thing done millions or billions of times, and multiplying and adding huge grid of numbers, matrices, contacts, words, and whatnot. It's basically the same simple operation, but it is repeated across thousands or millions of elements. Same operation which a CPU was doing, but repeated across multiple blocks. And so that is where the GPU comes in play. The GPU is basically a graphics processing unit. And ideally it was started and it was basically built for only one job, which was basically painting pixels on your screen. That is what you would have heard, graphics card and graphics processor. Initially it was only for basically adjusting and painting pixels on your screen. So every frame in a modern video game means millions of pixels. That would need a certain sort of lighting, that would need a certain sort of color, shadows, and everything is applied in parallel to these pixels. So you don't want one smart chef, you would want an army of line cooks, each flipping the same burger over and over in a perfect way. So for example, inside a CPU, instead of a handful of like big cores, you would see a thousands of smaller, simpler cores, right? And these are basically designed to do the same kind of math on many pieces of data that the LLM or GPU is going to handle. So this is basically called data parallel computation. It's less about making one decision, but more about doing the same operation across a giant crowd or a giant context, right? So AI loves this. When an LLM runs, it needs to multiply huge matrices of weights by lot of activations, layer after another. Lot of context is coming into play. A lot of work is happening into play, and these operations, so-called like matrix multiplies, non-linear activations are happening, convolutions are happening, and these are exactly the kind of regular repetitive mesh the GPU is basically designed for, which is basically very similar to what real gaming looks like. So if you try to run a state of art model purely on CPU, like if you are running probably like a small AI model LLM on a CPU, and there are ways to do that, by the way, using tools like Allen Studio and Olama. But if you don't have a GPU and you run these on a CPU, you will see a lot of things would break. First would be your throughput. It would be painfully slow, right? It would be painfully slow to even get a simple answer. Your real time could take like minutes to build, even for a very simple context that you are asking. Probably you can start with the weather question, it will also take a lot of time. Energy and heat for your particular system. Your CPU will consume a lot of power because now you're asking it to do a lot of repeated multiple tasks in one go. Right? It's basically like asking a sports car to tow a freight train. Might be possible in a theory, but terrible in practice. So the GPUs solve these constraints with massive parallelism and high memory bandwidth. Right? They can move huge blocks of data in and out of their cores quickly, and they can keep thousands of tiny workers busy at the same time. That's why big AI clusters they just don't have one GPU. They actually chain hundreds of GPUs together. They connect them with ultra fast links. Funny part, the gaming and AI are like cousins to each other. So in gaming, what does the GPU do? The GPU takes a 3D scene, which is basically a geometry, a particular texture, also lighting patterns, and then it turns it into a 2D frame. Understand this. It's taking a 3D scene, but it's actually turning it into a 2D frame for your screen because your screen is two-dimensional. But it is doing it like 60 to 120 times a second. Right? This is basically the frequency, 60 hertz and 120 hertz that you would heard. It is a simple math on a massive grid of pixels. And in AI, then this GPU, what it can do is can take high dimensional tensors. Right? Tensors is basically a big block of numbers, which is basically representing language, vision, audio, everything. And then it starts pushing them through a lot of weights, like 10 to 100 times. It does a simple math on a massive grid of activations. So when you hear about this data center class GPUs, think of them as like industrial engines. They are not like small kitchen appliances anymore. So chips like Nvidia's got their H100 these days and A100, or even the AMD has got their MI series accelerator. So they are basically designed to move and multiply huge amount of matrices and data with maximum efficiency. On the consumer side, there are gaming cards, right? So for example, RTX 4090, like they're tuned for real-time graphics and also AI assisted effects. So even a graphics card like an RTX 4090 would actually do parallel computing for AI. How do you know which GPU is best for AI? So you look at few simple signals, like how many teraflops, and this word you would heard, teraflops. What is teraflops? Teraflops is nothing but trillions of operations per second. So it can sustain the kind of math AI really uses. How much high speed memory or VRAM it has, how fast that memory is, and how well does it connect to other GPUs in parallel. But basically, that's a rabbit hole of its own, and there are a lot of things in that topic: architecture diagram, memories, specifications, interconnected systems. So we're not going to go deeper into it, right? But just always remember that super intelligence is not floating into cloud. There's no cloud. It's basically running on a GPU which is humming away in racks somewhere in the earth, consuming a lots and lots of energy, which would be a topic for discussion in subsequent videos. Physics don't lie, and neither the maths behind AI. If you understand even a little of how this engine works, how your words become coordinate, and how attention becomes or behaves like gravity, and how context holds informational heat or enthalpy, you'd stop treating AI like magic and reduce your system entropy, and you'll start treating it like a disciplined instrument. And so I would really recommend stop guessing, start engineering. My name is Anand Arora, and this is Decode by Anand or D by A.